it's supposed to coordinate the nodes in accessing the medium to avoid collisions. Okay, so at least it should minimize the collisions in certain protocols. So that is the idea behind MAC sublayer. You can classify the MAC protocols into three broad classifications: random access, controlled access, and channelization protocols. So under random access protocols, there are Aloha. Under Aloha, again, you have pure and slotted Alohas, which were discussed in the last lecture. And today's lecture, we'll continue with CSMA protocol along with CSMA CD and CSMA CA, followed by controlled access protocols, which is reservation protocols, polling, and token passing protocols. That is today's discussion. And the channelization protocols were already discussed under physical layer. Okay, let us continue with the CSMA. So before going to CSMA, let me brief out about the last lecture protocols that were pure and slotted Alohas. So pure Aloha, the concept is that whenever the station has frame to transmit, it is allowed to transmit. It allows to keep its frame on the channel without, checking for anything. That whether the other stations are, transmitting the frames or not. So you need not to check anything like that. So just you keep your frame on the medium. So if you get a ACK, it means that your frame is successfully received. Otherwise, it is collided with some other frames. That is the assumption that you have. So with this concept, the pure Aloha, the vulnerable time was twice the frame transmission time, and the throughput is at most 18.4%. Right? So that maximum throughput that you achieve when the load on the channel is 50%. So that is G is half. So at that point of time, you will get maximum throughput. That is a maximum success you get. Same way in the slotted Aloha, we are including a constraint that whenever a station has a frame to transmit, it is allowed to transmit, provided it's supposed to keep the transmission only at the beginning of the time slots. Okay, so where the time for transmissions is divided into slots, each time slot is equal to frame duration. So all the stations are allowed to keep their frames only at the beginning of the time slots. That is the constraint that we have added for slotted Aloha. So with this constraint, the vulnerable time is reduced to frame transmission time. Instead of twice the frame transmission time in pure Aloha, the slotted Aloha, it says that the vulnerable time is only the frame duration, and the maximum throughput that you can achieve is 36.8%. So that is at the load is 1. So that means the 100% utilization of the channel with the load equal to 1, then you will get the maximum throughput in the case of slotted Aloha. So that was the discussion that we have done in the last lecture. Today's discussion will continue with CSMA protocols. So where the concept behind CSMA, carrier sense multiple access, is that you just sense the channel or sense the medium before you start your frame transmission. So in simple understanding, listen before you talk. Okay, so before listen means you listen to the medium. So whether the medium is already engaged in others, frames, or the medium is idle. So just you try to listen to that. If the channel is idle, then it's a clever idea that you can transmit. Otherwise, you have to defer. So that is the fundamental principle behind CSMA. That is, carrier sense multiple access, sense the channel before you start your frame transmission. So whether this really avoids the collisions, that we have to inquire now. So carrier sense multiple access. So I have, being a station in the network, I have a frame to transmit. What I supposed to do is, first I should listen to the medium. So whether the medium is carrying the frame bits or not. So if it is carrying, then I should wait. Otherwise, I can transmit. So keeping this in mind, you try to explore this example and understand really this avoid collisions. So now I have four stations A, B, C, D, and the station B is starting a frame. So of course, before it starts its frame, it will sense the medium. So since nobody is attempting the channel, so before T1, so when B senses the channel, it looks ideal. So it can start its transmission. So the yellow colored part is, the frame transmission. So at time instant T1, station B has started its frame. So obviously, when it starts its frame, it takes time to transmit all the frame bits, and each bit will travel with a certain propagation delay. So that's why you can see the slant line both on towards A as well as towards C and D. Okay, so that propagation delay takes. Now the first bit of frame B reaches first at node A, and it takes more time to reach at node C, and it takes longest time to reach node D. Okay, so this is about frame B. Okay, so B has sensed the channel at time instant T1, and since the channel doesn't carry anything, so it seems to be idle, so B can start its frame. So, and the frame bits takes some amount of time to reach the other nodes. Meanwhile, the B is continuing its other frame bits. Okay, so the first bit reaches first, right? So that yellow color you can see. So fine, now you should be very careful in observing this diagram that, so when the first bit of the frame B reaches at C, so whether it is before time instant T2 or after the time instant T2, that's the question I am asking you. So the first bit of the frame B has started at time instant T1. Because of propagation delay, it takes some amount of time to reach the other nodes. Okay, so my question here is, when the first bit of the frame B will arrive at station C and D, whether it is after T2 or before T2.
Before T2, sir.
Try to understand, try to observe the figure and tell me carefully.
Sir, it will be after T2 as time is moving forward downward.
Yes, time is downwards. The axis of time is downwards. So the slant line, it means that there is a propagation delay. So now you can see the yellow color you cannot see at node C and D because it's overlapped colors, blue and yellow. So it looks something like towards gray colors actually. Fine. So now the first bit of frame B arrives after time instant T2, both at C and D. Okay, the first bit or the initial bits of B arrives at node C and D after the time instant T2. Do you agree with this?
Yes, sir.
Yeah. So now, since the bits arrives after time instant T2, so if node C senses the carrier at time instant T2, so what is the result at node C? Node C is sensing the channel at time instant T2. So what is the channel condition at node C at that point of time? Whether the channel looks engaged with frame B or it looks ideal?
It looks idle for C. That's why it starts trending.
Exactly correct. So at time instant T2, when node C sends the carrier, it looks ideal. But the fact is that the channel is already started, carrying frame B. Because of propagation delay, C could not realize about it at time instant T2. So C has started its frame. Because the channel looks ideal, it can start its frame. So immediately after its transmission, what's happening? There is a overlap of frames that belongs to B and C. So now none of the corresponding receivers can make use of these frames. So here the catch is that even though you are following CSMA concept where you are, knowing the carrier status before you start your frame, but still it may leads to collisions. What is the reason behind this?
Sir, because of the propagation delay of B, that's why C starts sending.
Perfect. So here we are unable to, identify the collisions when you are sensing the carrier because of propagation delays. It is because of propagation delays. So what is the worst situation here? What is the maximum propagation delay in this example?
Sir, only B will be able to transmit to A. That's the only possible scenario. But when it transmits towards C, there will be a collision of frames.
Okay. Now my question here is that here I have taken an example of 4 nodes and B has sensed the channel first and it has started, after that C. So but there is other combinations also. So A can also start sensing first, or D can also start sensing first, or C also can start sensing first, later the other nodes. So like that. So there will be various situations, but always we should try to focus on the worst situation. So what is the worst situation here? The longest propagation delay. Okay. So assume that A. Okay. So A has sensed the channel first and it has started its transmission. So now who will realize that frame A that is carried by the channel? So which node realizes first?
B.
Node B. So
B
later C.
realizes first.
Yes, exactly. Node B realizes first, then C. At last, node D will realize. Now, what happens? Just just before arrival of the first bit of frame A at node D. Okay, try to understand. I am discussing the worst scenario in the network. So A and D are the two nodes which are far away. Okay, so at the two extreme ends of the network. So A sensed the channel, it looks ideal, so it has started its transmission. So the first bit or the initial bits of the frame are just about to arrive at D, just about to arrive at D, but just before that D sensed the channel and it looks ideal. Okay, so now what will happen? Immediately after D's transmission, the first few bits, there is a collision. There is a collision. But these nodes are unable to, realize about it. So that's the worst scenario here. So I'll discuss the same example in more detail in the next slides. Okay. So here, try to understand that even though you are sensing the carrier before you start your frame transmission, but still it will maybe really reduces the number of collisions compared to allohas, but still there is collisions. There is a chance of collisions. So this is another example. So you can see there are 4 nodes. B has sensed the channel at instant T0 and it has started its transmission, and immediately after that, T1 has sensed node D has sensed the channel at instant T1, where the frame bits of B are yet to arrive at node D. So they are yet to arrive. So when node D sensed the channel at instant T1, it looks ideal. So D also started its transmission. However, both the frame bits got collided. You can see the overlapped area. So this area is collision of the frame bits that belongs to node B and D.
So I had a doubt.
Yes.
So couldn't we, if you go back to can you go back to one slide, the previous slide?
Tell me.
Sir, in this, if we assume the worst case scenario that A starts transmitting at T naught, so, listen,
Yeah, go ahead.
if A starts transmitting its bits at T naught, so shouldn't we keep a buffer time, so that if we keep that buffer time, then no collisions, like we can achieve an ideal situation in which we can avoid some collisions.
Okay, so how other nodes can understand that A has started transmission?
So, for example, if we take the like A to D as the worst case scenario, and if we take some buffer time as some greater time than T naught, like T2 minus T naught, if we keep it as a buffer time, so if D will sense whether it has received A's bits, after that only it will start its transmission, because in this case it's not happening like that.
No, here the concept that you need to understand is that there is no any control, or there is no any monitoring of of the nodes in the network. Okay, so you do not know what other nodes are doing. So whether they are sensing the carrier or whether they have transmitted the frames, that you do not know.
Okay, sir.
No, please, if you are not convinced, please tell me. I will try to address it. Here, the
I got
medium axis, the concept is that the nobody is there to control the network. That you are allowed to transmit now, and after that you should wait, or like that. There is no any constraint as such. If you look at the name of the protocols that we are discussing, it is a random axis. Random in the sense it is a probability based actually. So all the success for our frame transmissions depends on the probability. So you cannot give guarantee that your frame is going to get success now. You cannot give guarantee for that. So all the things are based on the probability. So nobody is having control over the network about the axis. So which node has to access when? Nobody has control over that. So that is the scenario here. So now can you repeat the question?
So my question was, the worst case scenario was from A to D, right? So if
Yes.
we take frame transmission time from A to D as buffer, then we could avoid certain collisions.
How?
Uh, so I will discuss it later.
No. Go ahead. Let others also understand it.
So if A starts, if we assume that A has started its transmission first,
Okay.
and if D also wants to transmit simultaneously, so if we take this buffer time, which was not earlier the case, if we take this buffer time, then D would have received the A, like D would have sensed that it's occupied, the channel is occupied, and then after that it will start transmitting, hence avoiding collision if we take the buffer time in this case.
No, how you define this buffer time?
So buffer time is calculated between the worst case scenario, between D minus A, like the maximum time that can take between D and
So
A.
yeah. So let's come to your point that A to D there is let's say some 5 milliseconds first propagation delay. Okay.
And yes,
So
after
yeah. So what I understand, I will tell you. So you are telling that A has started at time instant T0 and till 5 milliseconds, nobody else should start.
Yes, sir. So that they can all sense the channel. For example, in the worst case, if D wants to transmit, so after 5 seconds, it can sense whether or not A has sent, and then
Yes.
everybody can.
But, yeah, agreed. But there is no any such constraint here. There is no any constraint because
Got it. So that's why you told it's probability based. That's why
yes,
I told.
B, C, D, they do not know anything that A has started until unless they receive the bits.
Got it, sir.
Okay. Yes. Fine. So now the worst case scenario, as we have discussed, that when you can detect the collisions, that's the important thing that you need to understand here. So vulnerable time. So as you are telling the buffer time, I am coming to that point. So in this case, what is the vulnerable time? So vulnerable time is the longest propagation delay that is present in the network. So why it is like that? Can someone justify it?
So because vulnerable times definition is that after this time we can guarantee that like we can transmit successful bits like without any collision. So if
Yes.
we are
Yes.
able to
Yeah.
get this time, then
Yeah. So here the vulnerable time is that so the duration of the time where there is a more probability that your frame is going to get collisions. Okay. So if you overcome that time, then you will get success. Okay. So at time instant T1, right? So A is going to start, let us say. So then, if no other stations attempt to transmit at least for the longest propagation time, then frame A is going to get success. So if any of the nodes are trying to attempt during this vulnerable time, then you will not get success. Okay, so the vulnerable time in a CSMA is the propagation time. So what is that propagation time? The propagation time between two extreme nodes in the network. So which is nothing but the longest propagation delay in the network. That is your vulnerable time. Okay. So now this CSMA is described in multiple ways, called a one persistent, non-persistent, and a P persistent CSMAs. Okay. So what exactly these are? Let us look at one persistent. You continuously sense the channel. So obviously you know the concept of CSMA that you have to sense the channel or carrier before you start your transmissions. So that check, you do it. You do the the channel or carrier status. If it is idle, then you can transmit your frame with probability 1. Okay, so that means there is no any ambiguity for you now. So as and when you find that the channel is idle, you can start your frame transmission with probability 1. If the channel looks engaged, if the channel is already carrying others frame bits, then you need to wait. You need to continuously sense the carrier till it gets idle. Okay, so you are going for a continuous check. Now coming to non-persistent or zero persistent, this is called zero persistent. So you check for the channel status. If it looks idle, again you can start your transmission. You can start your transmission. If the channel is engaged, if the channel is already carrying other station frame bits, then you wait for some random amount of time before going for next attempt of checking the channel status. Why should we do this? Can someone answer? So in the one persistent, what we say is you continuously check for the channel condition till it gets idle. Non-persistent, what we are saying is if the channel is engaged, okay, so if it is busy, so before going for the next check of the channel status, you wait for some random time. Why do we do this?
So is it because that checking the channel requires some amount of energy, so you don't waste energy?
Yeah, so it is a common sense to understand that there is no use of continuous checks. Okay, so for instance, if we say a frame duration is let's say 5 milliseconds. So during the 5 milliseconds, if you are continuously checking but still you don't get ideal condition at least for 5 milliseconds. So the clever idea is that when the channel is engaged, it's better you wait for at least 5 milliseconds, then go for next check. So that reduces, as you said, Abir Shankar said that it reduces number of checks. Obviously, it reduces. Okay. So that is called non-persistent. Now there is something called a p persistent. So non-persistent is 0 persistent. The probability value is 0. 1 persistent is probability value is 1. Two extremes. Now a p persistent. So p persistent. So the value of p is between 0 and 1. Now coming to this p persistent strategy, how it works. So you check for the channel status. If it looks idle, right, then you can start your frame transmission. Okay, so with a probability p. You try to understand, it's a little tricky. So if the channel is idle, in the previous two cases, what you are doing? You are transmitting the frame without any ambiguity. But here, I'm not sure that even though the channel is idle, but I'm not sure that I can transmit the frame. So what I'm doing is I'm, choosing the probability. So let's say p value is 0.5. So then how to understand it? If the channel is idle, then only 50% of chances that I am going to transmit my frame, and the rest 50% I'm going to wait. So wait, again you check for channel status. Okay, so if still the channel is idle, then you can transmit a frame with probability p again. When during the second check, if the channel is engaged, so then you should wait for a back off time. So back off time is exponentials of 2, binary back off, which we have discussed in pure aloha. Okay, so here you are, even though the channel looks idle, but still you are not sure that you are going to transmit your frame. So, and you are going for second check of the channel status for some amount of p value. Why do we do this? So is it a clever idea? So when the channel is idle, why you are not rushing towards transmitting your frame? Instead, why still you are thinking of with some probability?
So because here we are taking the propagation delay into picture.
Okay.
Sir, also there are multiple nodes present. So
Yes.
we are considering what is the probability that if we transmit it now, another node might also transmit it during the time it will take a frame to go from one node to another node.
Perfect, perfect. See, here I am doing multiple checks because the same story is repeating at all the nodes, whoever wants to transmit the frames. So I am checking the channel, it looks idle. Even for the other node also, it looks idle. So, both the nodes, when they transmit, again, it leads to collision. Which we have discussed under the, basic CSMA. So that's why we are trying to avoid collisions. So we are taking more precautions, more safer side we want to be. So that's why we are going for the next check. Okay, so second check also we are doing after some random time. So this reduces, the number of collisions, but at the same time, you are paying for link utilization. So try to understand that aspect also. So how it, reduces the link utilization. You see this scenario in the first check, when you are initially checking the channel, it looks idle. So, but still you are not sure that 50% chances that you are going to transmit and 50% you are not going to transmit. Let us take that. So 50% you are not going to transmit, you are going to wait. So you are going to wait for some slots time. Okay, so wait a slot. You can see in the flow chart that wait a slot. This number of slots will increase in powers of 2 for every attempt. Okay, so after waiting that much amount of time, you are going for second check of the channel status. So now the channel is idle again. So what you are doing? So you are going to transmit a frame with again a probability based. So even in 2 checks, you realize that the channel is idle, but still you are not transmitting. So you are not effectively utilizing the channel. The channel is idle, but still you are having a hesitation to transmit because you are, feeling that your frame gets going to be collided with others. So that's your worry, but still, so the link utilization aspect, so it will reduce. The link utilization will reduce. Of course, the reality is that when you want one thing, you have to pay for the other. So when you want to reduce the number of collisions, so you are paying for link utilization here. Yeah, the same flowchart in different representations. You can see here the first figure that one persistent. So you are going to continuously check the channel till it gets idle. So once the channel gets idle, then you are going to transmit immediately. The 0 persistent or non-persistent, you are not going to continuously sense the carrier. Instead, you are going to sense at regular intervals. What is that regular intervals? You see this second figure, non-persistent. First attempt you are making in sensing the carrier, it looks busy. So what you are doing for some amount of time and going for second check. So the second check also looks idle, engaged, right? So it is busy, the channel is busy. So then what you are doing, you are going to wait and you are going for the next check, the third check. So can you identify the time difference between first check to second check and second check to third check? What is the difference that you can identify?
That is approximately double.
Yes. So it's more than that, right? So it is, binary exponential, in fact. Fine. So the random amount of time that you are going to spend before the next check, okay? So it is exponentially increased when you are facing the channel is busy. Okay, so this is not the story when the channel is idle. So when the channel looks idle, immediately you are going to transmit. Fine. Now coming to P persistent. So here you are doing 2 different things. One is continuously you are sensing like one persistent. So after after the channel is idle, but still you are not going to transmit. Instead, you are waiting for different time slots. Okay, you are going to transmit with the probability P, or you are going to wait for time slots and go for next check, and then you transmit. So that is how the P persistent works. Yes, this is the theory behind our discussions. So you can realize that all the strategies, one persistent, P persistent, zero persistent, or non-persistent, all they have their own advantages and disadvantages. Okay, so collisions will be more. If you want to reduce the collisions, you have to pay for link utilizations. Okay, so this is a predefined formula. So there is a minimum derivation behind this, but we are not interested in deriving the link utilization. Instead, you can take it as granted that G is the load and A is T prop to T frame. So same as the previous definitions, the alpha. Okay, so the alpha parameter is the ratio of T prop to T frame, and G is the load on the channel. So this load is contributed by the fresh frame transmissions, also the retransmission of the failed frames. So G into e power minus G alpha over G into 1 plus 1.75 alpha plus e power minus G alpha. So that's the link utilization for non-persistent CSMA. And this slide I am keeping because it's not a big deal to program these protocols. Okay, so this is some sample program to simulate the protocol and understand its performance. Okay, so here it's a combination. You can see here Aloha protocol with P persistent. So the maximum number of nodes is 100. Okay, so and the number of slots. So P persistent, you have slots, right? So I'm not going to explain the program as such, but here you need to understand that you can do it easily if you are quite familiar with C or CPP. Okay, that's fine. Let's compare the performance of all the protocols that we have discussed. Starts from pure Aloha to slotted Aloha and CSMA with different persistent strategies. So you can see the p value when p is 1, you can see 1 persistent CSMA, and p is when you are decreasing. So you can see you are getting a higher throughput. Can you observe it? So P is 1. So it is better than slotted Aloha? No? Yes. So the poor performance you can expect from pure Aloha, and double the performance you can expect from slotted Aloha. Even you can get a better performance than Alohas with 1 persistent CSMA. And when you decrease the P value to 0.5, still you are getting a higher throughput. And when you decrease the P value to 0.1, you are getting more throughput compared to all these previous things. And when you decrease further to 0.01, so you are getting the highest throughput. And P equal to 0, which is a non-persistent, it is in between 0.1 and 0.01 persistent strategies. So this is the throughput performance of different Alohas as well as CSMA with the different strategies. Okay. So now, how you are going to address the collisions? So when your frame gets collided with others' frame, how to realize about it? So how you can realize that your frame is getting collided with others? So that is the concept behind CSMA CD. Okay, so CSMA fundamentally we should do what we have discussed. The same thing we have to repeat. Apart from that, okay, so you should also do collision detection. So for simple understanding, you can take it in this way, that listen while talking. Okay, so simple CSMA, what it says: listen before you talk. Listen before you talk. Now listen even you are talking. Okay, so listen to others. Listen to others while you are talking. So both you have to do here. That is the CD component. So this is the actual MAC protocol that you use in wide LANs. All the wide LANs which we install in our laboratories and all that stuff. So that which is called Ethernet, we follow the CSMA CD protocol. So IEEE standard for this is IEEE 802.3. So it's a wide LAN MAC protocol. So the concept behind this is carrier sense multiple access with collision detection. So first you have to perform CSMA, that is carrier sense multiple access. Just you sense the carrier before you do frame transmission. If the carrier is idle, then maybe if you are following simple CSMA, then you can start your frame transmission. If you are following any persistent strategies, accordingly you have to start your frame transmission. So with CSMA, you are going to transmit your frame. So once you start your frame transmission, you should also listen to others. So whether other nodes are keeping quiet or whether they have transmitted the frame. So why we should listen to others is to know about the collisions. So we should know about the collisions. So once we know the collisions, that it means that once we realize our frame is getting collided with others' frame, then there is no point of continuing my frame transmission. Immediately I can stop it because it is not going to help my receiver. So my friend is not going to make use of my frame because it is already damaged with collided with others frame. So clever idea is better you stop transmitting your frame transmission frame bits. And also if you are so having helping nature, then you also do that jamming signal, which is a 48-bit special sequence. You try to transmit this sequence in the network so that other nodes will come to know about this and they will understand that there is a collisions. So they defer their transmissions. So that reduces the number of collisions. So that is called jamming signal. Okay. So what you should do, using CSMA component, you start your frame transmission and also you listen to others so that you will come to know whether your frame bits are getting collided with other frame bits or not. So if your frame bits are getting collided with other station frame bits, then immediately you stop your transmission. You abort your transmission and generate a jamming signal and circulate it in the network so that other nodes, when they observe this special 48-bit sequence jamming signal, they will understand that there exists collisions. So better let us defer the frame transmissions. So that is how you can help other stations with jamming signal. So this is the flowchart for that. You can see K is the number of attempts, and so you using CSMA with the different persistent strategies. You can follow. You pick up one of the persistent strategies to transmit your frame, and while transmitting your frame, try to listen to other stations for collisions. If there is no collision, then your frame gets success and you can go for the next frame transmission, as simple as that. But Unfortunately, if your frame is getting collided with other frames, then immediately you should stop. You should stop your frame transmission and send a jamming signal to other stations, and repeat the attempt. You can go for the next attempt by following the back off strategy. Okay, so you can see here in the flow chart, the left side, whatever we are seeing here, these things are already discussed under pure aloha in the last lecture. So it's a common thing for all the random access protocols that whenever you get a failure, then before going for the next attempt, make sure that the number of attempts is at most 15. So it should not cross 15, and pick up one value, right? A random value between 0 and 2 power k minus 1. So in that range of values, you pick up one value and multiply with either a propagation delay or frame transmission time, and wait for that much amount of time before going for next attempt. So this is a binary exponential back of time. So this is a common story in all the protocols. Okay, so now so how to detect the collisions, and what is the condition to detect the collisions? It is not just like that you can detect it. So how exactly you are going to detect? So that we are trying to understand here. So in this example, there are 4 nodes A, B, C, D, and the time instant T1 where A has started its frame bits, and at time instant T2, C has started its frame bits. Because so when C senses the carrier, it looks idle at time instant T2 because A bits are yet to arrive. The first bit of frame A is yet to arrive, so it is arriving at T3, but T2. So T2 is earlier than T3. So when C senses the channel, it looks idle. So it has started. So now, since we are also handling CD component, collision detection component, so C can immediately realize about the collisions as and when the first bit of A arrives at C. So the first bit of A gets overlapped with the frame bits of C. So C is going to realize about the collisions, and it will stop its transmission. It is not going to transmit further frame bits. But what about C? What about A? So A is not realized about collisions because the C bits are yet to come. So unless the C bits comes at node A cannot realize about the collisions, right? So whenever there is a overlap of 2 different frame bits, then only you can realize the collisions. Otherwise, you cannot. So when there is no overlap of bits, you cannot say that it is a collision. So now I am going to pose a question here. Carefully understand this. So C, the first bit of frame C is going to arrive at time instant T4. Okay. So A has started its frame transmission at T1, and the first bit of A is arriving at node C at T3. And before T3, when C senses the channel, it looks idle at T2. So C also has started the frame transmission. However, after arrival of the first bit of A at node C, C has realized about the collisions, so it has stopped its frame transmission. But node A is yet to realize about the collisions. So A is going to realize about collisions at time instant T4. Okay. So then it is going to stop. Till that, A is going to continue its frame bits, transmitting the frame bits. Any doubt till this point?
No, sir.
No. So now I am trying to pose a question that what should be your frame size? what should be your frame size? Why I am asking is, when station A started its frame transmission at instant T1, it can detect the collision. It can realize the collision. Collision is already happened. But in order to realize the collision at node A should transmit the frame bits at least till T4, where the first bit of frame C comes. Till that, frame A should continue its transmissions. Then only at node A you can find the overlap of frame bits. Otherwise, there won't be overlap. For example, so if node A completed its frame transmission, before T4, so after that frame C bits are arriving at T4, so A cannot realize the collision because there is no overlap. But what is the fact? The fact is that already A and B frame bits are already collided in the network. Unfortunately, A is not going to realize about it because it has finished its frame transmission before T4. That means before arrival of C bits. Before arrival of C bits, when A completed its frame transmissions, it cannot realize the collisions. So that's why what should be the criteria in order to realize the collisions? Can someone answer this? Just think of it. Is a little tricky.
The T frame should be much greater than T propagation.
T frame should be much greater. Okay. So that means you need to maintain a very large frame size. So that T frame will be higher compared to T prop. Is it so? Yes, that's the correct answer. But longer frames we cannot handle, right? So we know the situation that during framing the initial aspect of this chapter we have done. Why should we cut the packet into frames? So we cannot handle larger frames. So what should be the minimum frame size at least?
Equal to T prop.
Is equal to T prop. Just think of how it helps you to realize the collisions. Okay, so let us assume that T prop. So T frame should be at least T prop. Is it so? Okay, so keeping that in as a that criteria. So let us take A has started its transmission. A has started its transmission. And worst scenario we should adjust. Okay, so A and D. So A has started its transmission at T1, and it reaches at the end to node D, right? That's the worst scenario. The first bit of A will arrive at node D. So by the time it covers all other stations. Now at node D, just before arrival of the first bit of A, listen carefully, at node D, before arrival of the first bit of A, when D senses the channel, it looks idle. So D can transmit its frame. So once it just started its frame transmission, the first bit of A will arrive at D. So D will realize the collision immediately. What about A?
He will realize it later after sending all of its.
No. See, I'm giving half of the answer. See, A started its frame transmission at time instant T1, and it takes the propagation delay. Okay, so propagation delay means the longest propagation delay I'm talking, because I'm considering the worst scenario, which is the A and D, two extreme nodes in the network. So the propagation delay between nodes A and D is the longest propagation delay. So when node A started its transmission at T1, it takes T1 plus T prop to arrive at node D. Okay, so just before that time, when D senses the channel, it looks ideal. So D also started its transmission, but immediately the first bit of A came, and D realized about its collisions, because it is it is listen while talking. That is the concept. That means apart from frame transmission, it also listen to collisions. So that's how D realized about the collision immediately, and it has aborted the transmission. Now, what about A? In order to realize the collisions at node A, what should be the condition? Am I audible? Hello?
Yes, sir, but it's like I'm not able to get it. Like the answer to the question.
Come again.
You are audible, sir, but I'm not able to get the answer to your question.
Okay, okay. Anybody else? When A is going to realize the collisions, or in order to realize the collisions at node A, what should be your frame transmission?
Sir, is it the frames transmission plus the propagation time?
No. See, one thing is, when you start the frame at time instant T1, it takes T prop to reach at D. So after T prop, D is going to realize the collisions. So the first bit of A is arriving at D after T prop. Same way, the first bit of D is going to arrive at A after, again it takes another T prop. Yes, exactly. Altogether it is twice the T prop.
Also two T.
So yes, till that A should continue the frame transmission. Then only there exists a overlap.
Sir, but we cannot increase the frame transmission time because then the frame size would increase, right? You only told.
That is what. See, when a T prop is less, then twice the T prop also will be less, which is a T frame will be less. But the minimum size the minimum size of the frame you need to maintain such that it should be, the frame duration should be at least twice the T prop. Then only you can able to detect the collisions.
Yes.
Otherwise, you cannot detect the collisions. Okay, so here the catch is that in CSMHCD, in order to realize the collisions, the frame size should be at least, the frame size in the sense of frame duration should be at least twice the T prop. So that is the catch of this discussion. You can raise still if you have any queries related to it. So I don't know why I'm stuck. I'm unable to, my slide is unable to move forward. Okay. Am I audible?
Yes, sir.
Yes, sir.
Okay, that's fine. That's fine then. Yes. Yeah. So now let you understand. There are three different things in the channel. So either the channel is carrying the frame bits. That is one situation. Either the channel should carry the frame bits, that is a frame transmission, or it is in the waiting state. So that is called contention period, and the waiting state will be defined in contention slots. So either the channel is carrying the frames, or it is in the waiting state, or the channel is idle. These are the three possibilities. Okay, so this is important for you to understand further. The channel, either the channel is idle, that is one possibility, or the channel is carrying frames, or the channel is waiting state. Waiting state in the sense, the channel is idle, but you are not sending, so you are waiting. So these are the possibilities. Yes, this is covered. The vulnerable time in CSMA is T-prop. Yeah. So can you quickly answer this question? In a network using CSMA-CD has a bandwidth of 10 Mbps, which is a standard Ethernet. So if the maximum propagation time, including the delays in the devices and ignoring the time needed to send the jamming sequence, is 25.6 microseconds, what is the minimum frame size? That's the question. So the maximum propagation time is given as 25.6 microseconds. The question asked is, what is the minimum size of the frame? The protocol mentioned is CSMA-CD. So that means you should be able to detect the collisions. In order to detect the collisions, what should be your minimum frame size? So what is the T frame here? What is the frame transmission time? As per CSMA-CD?
2 times the propagation time.
Exactly correct. 2 times the
Propagation time.
propagation time. So what is that time? It is 51.2 microseconds, right? Twice the T-prop. T-prop is 25.6 microseconds. So twice the T-prop means 51.2 microseconds. So now, you know that bandwidth is 10 megabits per second. So per second 10 megabits per 51.2 microseconds. How many bits? So that is how you can define the frame size. So that is 64 bytes. So which is nothing but 512 bits. So this is the minimum frame size. So should be 512 bits. So in CSMA CD, that is nothing but standard Ethernet. So as I told you, 10 Mbps means, if you remember when we are discussing the physical layer, we have discussed the Ethernets, the classification. So a standard Ethernet, the bandwidth is 10 Mbps. So with 10 Mbps, the frame size, minimum frame size you need to maintain is 512 bits in order to detect the collisions. Any doubt in this? So same way, can you tell this? CSMA-CD 1 Mbps bitrate, maximum network span of 10 kilometers with no repeaters. And propagation delay is 4.5 nanoseconds per meter. So per meter delay is given. So for 10 kilometers, you define the delay, that is your T prop. And twice the T prop is your T frame. So that T frame multiplied with the channel bandwidth gives the frame size in bits. So 4.5 nano, 4.5 into 10,000.
Sir, is it 45?
45?
45 bits.
45 bits. Is it so? Let me check. 45 micro. So 90 micro. 90. No, I'm getting 90 bits.
Yeah, sorry, 45 into 2. Yeah.
Yeah, it's a twice T prop, right? It's a twice T prop. T prop is of 45 microseconds. Twice the T prop is 90 microseconds. So 90 microseconds into 1 Mbps. So it is 90 bits. That is the minimum frame size. Yes. Okay. So can you answer this? In CSMA-CD LAN, 2 kilometers using copper wire running at 100 Mbps, what would be the minimum frame size to detect the collisions?
Propagation time, sir.
Yeah, that you need to calculate. Sufficient data is given to you. 2 kilometers is given and it is mentioned that copper wire. So what is the velocity of the signal in copper wire? In the physical layer, I have clearly told the velocity of the signal in copper wire is, sorry, ROE. Can you tell what is the signal speed in the copper wire? ROE Prashant.
2/3 of speed of light.
Exactly correct. It's a 2/3 of velocity of light, which is 2 into 10 power 8 meters per second. Okay. So distance is given and velocity is given, so you can give the time. What is T prop?
Two into 10 power 8.
Hmm?
T propagation time, right? It's 2
Yes.
into
T prop is?
the propagation time in copper wire, 2 into 10 power 8.
That is fine. I am asking propagation time in the network. It's given at 2 kilometers, right? The length of the network is 2 kilometers.
So 10 microseconds.
10 microseconds. Okay. So now what is your frame duration? T frame is how much?
20 microseconds.
20 microseconds. So what is the frame size now in bits? The bandwidth is
2000
given as
bits.
2000
bits.
2000 or 200? Yes.
Sir,
It is 2000 bits. Exactly. Okay. Yes. So this is the efficiency, the maximum efficiency of CSMA-CD is T frame by T frame plus overhead. So this you need to understand. The overhead is, the average contention interval, because we don't know how much time you need to wait to get success. So keeping all that in mind, so 1 by 1 plus 2a over capital A. So small a is the T prop and capital A is the probability that a station can successfully transmit in a slot. So the probability value, and A is, it is not the ratio as we defined in the earlier lectures. It is A is just a T prop. So previously we had defined A as a ratio of T prop to T frame, but in this formula it is just a T prop. Yes. So now try to understand physically how you realize the collision. So how exactly a station comes to know about the collision of frame bits. See, the when you sense the medium, so end of the day it's a matter of voltage signals, right? So in the medium, in the cable, you can see if the signal energy is uniform, like showing in the blue color, it means that the medium is carrying a frame. If the signal energy is 0, it means that the channel is idle. Now see this red color, that the signal energy is much higher. Okay, so it is double that of your frame energy. Okay, so it means that there is a collision. So if the energy levels are very high compared to your frame bits, then it is, you can conclude that there exists a collision. Okay, that is about realizing the collisions physically in the wire. And you can also see the channel, as I told you, either it is continuously sensing, right? So found busy. This is quite interesting. We are moving towards CSMA CA, carrier sense multiple axis with collision avoidance. With collision avoidance, we are trying to avoid the collisions. Okay, so how it works, you see here, you are continuously sensing the channel. It's a CSMA. So what CSMA, can someone answer this? What is the persistent strategy I am using here?
So one persistence.
Exactly, it's a one persistent CSMA I am using. So it says that you should continuously sense the channel till it gets idle. So once it gets idle, I am not going to transmit my frame. What I am doing, I am waiting, IFS, interframe space. Okay, so this is called interframe space. This is a one sort of waiting time. Okay, after IFS time, what I am doing, I am entering into this yellow window, that is, you can see these slots. Okay, this is called contention window. So where a group of slots is there, the contention window is a waiting time again. Okay, this is also waiting time. That waiting time is defined in terms of slots. You can see that yellow slots. So these yellow slots will continuously increase with respect to binary exponential. Okay, so initially I'll wait for 2 power 0 slots. Okay, so after 2 power 0 means one slot I'll wait, then I'll transmit my frame. So you can see send frame. So and once I send, I'll expect ACK. So my retransmission timer will activate, and if the timer's time is out and in that time I didn't get any ACK, now what should I do? I should go for retransmitting my same frame. So now repeat the story, that you go with CSMA and wait for IFS time. Now coming to this contention window, now your waiting time is 2 power 1. That means 2 contention slots you are going to wait before going for second attempt. So like this, so when you go on getting continuous failures, and when you are moving for the next attempt, the contention slots in the contention window will be increasing binary exponentially. So here the main difference is that the waiting time, even after the channel looks idle, before going for frame transmission, you are waiting. That waiting time is defined in two ways. One is the first stage is interframe space time, and the second level of waiting is in terms of contention slots. So this is CSMA CA. So that hopefully, try to avoid the collisions. So let me go to the flow chart. Yes. So here the IFS time, as I told you, interframe space. So that is again described in two ways. One is DIFS time, which is called a distributed coordination function, DCF, interframe spacing. So that is actually a huge value. So huge in the sense compared to short IFS. Okay. So another one is a short IFS time, okay, which is a smaller duration compared to DIFS. So this is how we define the IFS time. So now coming back to the flow chart of CSMA, how it works. Let us start. Set back to back of time is 0. Fine. Now you have to follow the CSMA. Here you can choose any persistent strategy, either P persistent or 1 persistent or 0 persistent CSMA. So after that, what you should do, you should wait for IFS time, that is called DIFS time. Okay. So as shown in the previous slide, the IFS time you have to wait, which is DIFS time. After that, what you are doing, you are sending request to send. So here you should understand, this is a very, very important, because the CSMA CA is used in wireless communications. So in wireless communications, there are two fundamental issues called a hidden terminal problem and exposed terminal problems. So what are those? That we'll sort it out using exchange of RTS and CTS. That is a request to send and clear to send. Okay. So assume that you have a frame to transmit. So in a wireless communication, what you're supposed to do is first you send a request to the receiver that you have a frame to transmit to the receiver. Okay, just like that, you cannot transmit a straightforward frame. After waiting for some amount of time, you cannot straight away forward the frame to the receiver. Instead, you have to transmit a request signal, that is called RTS, request to send. So once you send that request, then it will arrive at the receiver, and if the receiver is willing to receive your frame, then it will send CTS. Okay, so CTS is clear to send. So you should get, being a sender, you should get CTS within your timer's time. So once you get CTS, then you are going to wait for IFS time further. Got it? So what is that IFS time? You are going to wait for short IFS time. So you got the clearance that your friend is going to, he is willing to receive your frame. Okay, so that is the meaning of receiving the CTS. So once you receive CTS, still you are going to wait for some amount of time called short IFS time. Then you will transmit your frame. And once you transmit your frame, you obviously expect ACK. So if you get ACK, your frame is success. Otherwise, the binary exponential backoff algorithm will be repeated. So the left hand part, okay, the left part of your flow chart, that is increment backoff. That means your attempt K value will increase, and K will be compared with 15. So if it is less than 15, again wait backoff time, that is 0 to 0 and 2 power K minus 1. So the R value will be picked between this range, and it will be, the R value will be multiplied with either T prop or T frame, and that is your backoff time. And the story repeats. After waiting for the backoff time, again you will go for a persistent strategy, this flow chart, it will be iterated. Fine. So now, if you do not get CTS, okay, so you have sent request to send to the receiver, so, and the receiver did not give clearance. It means that it is not willing to receive your frame. So in this case also, you should wait for back off time and go for the next attempt. So here the understanding is that, so the difference between the previous flavors of CSM and this is that, so you cannot just straight away you can send the frame, data frame. Instead, you should send a request first. Okay, that is called a request to send. So for your request, if the receiver is willing, he will give the CTS. Again, that CTS should be within your timer's time. So then only you can understand that receiver is willing. If you don't get CTS within timer's time, then you should wait. You should repeat this story. Any doubt on this? You should understand what is RTS packet and what is CTS. So in wireless communications, the sender is going to send RTS first, and the receiver, if he is willing to receive the frame, then he will give CTS. Until unless he receives CTS, you are not allowed to transmit your frame. Okay, so if you understand this properly, I have a question to pose it. Oh, okay. Somebody is controlling my screen. I am unable to get it. Oh. So maybe I may take 5 more minutes extra, so that I want to cover the last part of CSMA-CA. Okay. How to move forward? So again, I could not skip straight away. So it takes a lot of time. Yes, 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 yes. It seems to be somebody is controlling this presentation. Okay, so let me pose a question that being a sender, so you know that when you want to send request to send to the destination, you are waiting for DCF IFS. Okay, so in short, DIFS time. So after sending request to send, the destination is waiting for some amount of time before giving a date to send. So here the first question is that why the destination is waiting to give CTS? As and when it receives the RTS, why it is not giving CTS? Instead, why it is waiting for some amount of IFS time, which is short IFS time? Can anyone guess? Hello, I am audible.
Yes, sir. We can hear you.
Yeah. Can someone guess why the receiver is waiting for short IFS time before sending CTS to the sender? That's the question. Remember, we are dealing with wireless scenario because CSMA is meant for wireless communications. So once you release the signal into air, you do not have control over it. And there is a possibility that other nodes also trying to release the signals, and both the nodes may be trying to reach the common node. All that is possible. So let me answer this quickly. That see, being a sender, you are sending RTS. That means you want to send some data frame to the destination. Same way, there may be other nodes who are trying to do the same. So there are chances that other nodes having highest priority compared to you. So destination takes time to collect such RTS packets from other nodes along with yours, and based on the priority, it will give the CTS. So that's why it takes time to give CTS. Fine. So now again, even after receiving CTS at the sender side, why can't you give us transmit data again? Why you are waiting for short IFS time at the sender side? Even you got the clearance from this receiver, so why don't you forward the data straight away? Instead, why you are wasting time? That's the question. So all these short IFS times that you wait is just to avoid the collisions. Okay, so it is just to avoid the collisions that happens. Okay, so that is about short IFS time. And when you discuss the wireless communication subject, you can explore these things in a detailed way. Okay, so this CSMSCA we have already discussed, right? So this is a back off story. Okay, so still ideal, then you wait for the back off time. This we have already done it. Okay, so then yes, so as I told you, hidden terminal problem. So here this is a wireless scenario. So you have, see, A, B, C, A and B. Okay, so these are the two nodes. That yellow circle indicates the communication range. When A releases the signal, at most it can cover that yellow circle. So to that extent, it can transmit the signal. Beyond that, the signal cannot transmit, cannot be traveled because of the limited signal energy. Same way C also. When C releases the signal, that it covers the yellow region. B is a common node which is present in the communication range of both A and C. Okay, so try to understand. So A doesn't know the presence of C. C doesn't know the presence of A. However, B knows the presence of both A and C. Okay, because it's a common node, so it is in the communication range of both A and C. Now, when A releases the signal, when A wants to transmit to B and C also wants to transmit to B, so they can transmit the frames, right? And there exists a collision at a common node, which is B. Agree? This is the general scenario. So hidden terminal problem is that in the wireless communication, when two nodes, they want to communicate to a common node. Okay, so then there exists a collisions. So we can avoid this by exchanging of RTS and CTS packets. So as I explained you that, so I can avoid collisions here. Let's say A is having data to transmit, it will send the request to send first. Same thing happens at C also. C also send RTS. RTS is a very, very small packet compared to your data frame. So, and RTS packet will be received at B from both A and C, and B is going to give CTS either for A or C. It cannot give simultaneously for both. So B is going to give CTS, let's say, for A. Then A is going to transmit the data and B will acknowledge. So after transmissions between A and B, then B is going to give CTS to node C. Then node C is allowed to transmit. So here, whether it really avoids collisions completely 100%.
Yes, sir, it should avoid because it's waiting for the proper turn.
Proper turn. Okay. Is there any other answer? Exchanging of RTS and CTS really it avoid collisions 100%. Okay, so assume that A and C are at equal distance from node B, and A and C at same instant of time they have released the RTS packet. What happens at B?
So
RTS packets itself gets collided, right?
Yes, sir.
Yeah, so again they need to retransmit RTS. So that's a worst situation I'm talking about. So we should think of that. So that's why it's a random access. There is no guarantee for collision-free things. That's the conclusion of random access protocols. Now coming to controlled access protocols. It's a very simple thing to understand. So here somebody is there, or some mechanism is there to control the sharing of the channel among the network nodes. So that's the concept of controlled access protocols. Here there is no much complexity like random access. So here there are three techniques. Let us think of that: reservation, polling, and token passing. So what is the reservation? So there is some frame, okay? So some frame called reservation frame, which is continuously present in the network, okay? So probably it will revolve in the network. In this example, there are 5 nodes in the network, and each node is assigned with 1 bit. Okay, so and this reservation frame is continuously revolving in the network, and whichever node has data to transmit, they have to enable this bit. By default, it is 0. So in this example, node 1 has a frame to transmit, then node 1 corresponding bit is enabled. So now the channel is allocated to station 1, and it is allowed to transmit. So in the next attempt, node 1, 3, 4 has enabled their bits, and the channel is allocated accordingly. So whoever enabled their bits, in that same sequence, the channel is allocated for them. Okay, so like this, is there any chances of collision here? Yes, quickly answer so that I can move to other slide. So there is a reservation frame. Whoever wants to transmit, they should enable their respective bit, and if they enable, then the channel is allotted for them. If more than one station enables, then in the same sequence 1, 2, 3, 4, first station 1, next station 2, station 3, 4, 5, like that the channel is allocated. The next one is polling. So polling is being a primary station, I will ask each secondary station whether they have data to transmit. So if they have, then they will send data. Okay. So otherwise they will send a negative acknowledgement that I don't have data. Then I will ask others. So polling means asking. So verifying the presence of data. So if a secondary station has the data, then they will send the data. And being a primary, you should send ASIK, something like that. Okay. So if you are sending a data, then they will send ASIK like that. So polling means asking. You remember in COA, you have discussed this. Interrupt implementations. Okay. So daisy chain and polling. So the polling means you are just asking whether you have a data. So if you have data, you transmit. Otherwise, say no. That is a negative acknowledgement. Then I will ask the other guy. So here also no collisions. So because the primary station is looking after the accessing the medium. The last one is called token passing. So token passing means a token. Token means a small 3 bytes, actually 24-bit packet, which is continuously revolving in the network. Okay, so a 24-bit length frame is continuously revolving in the network. Okay, ring. So whichever the station wants to transmit a frame, they have to grab the token and release the frame, data frame. Okay, so and that data frame will visit all the stations, and one or the other will be the receiver. So that frame will be received by the receiver, and the same frame will be back to the sender, because it is a ring in topology. Okay, it's a ring topology. So the sender will get back its own frame. So once he get back his own frame, he should keep that aside, means he should ignore it and release the token. And others can access the token whenever they want. They have frame to transmit. So like that, whoever has a frame to transmit, they have to grab the token first, and they can allow the they can transmit the frame. Unless you have token with you, you are not allowed to transmit the frame. So that is how token passing works. Is there any collisions in this? Please answer. Yes, Yuvraj Jain. Please answer this.
No, sir, we cannot have collision.
Yes. So in these three techniques, token passing we don't have, even polling we don't have, primary station is looking after, and also reservation frame we don't have any collisions. This is called controlled access or scheduling protocols. So that completes today's discussion. And there are a few examples, numericals, which I have given to solve. So that are mentioned, all the numericals. So I have uploaded in the Teams. Till today's lecture, all the PPT is uploaded, including the numericals, which are given as homework. Try to solve, and if you have any queries, you contact me. I'll clarify the answers for that. Okay. So till today's lecture, I have uploaded the PPT. You can see L7. L7 is the one which I have uploaded. You can